Welcome to another podcast. In this episode, we're going to be taking a look at how to calculate or evaluate definite integrals via a U substitution. The basic problem that we're going to be looking at here is how to evaluate the integral from a to b of a function of the form f of g of x times g prime of x dx. And remember, this is because we think of a U substitution or the substitution method as being the reverse of chain rule for derivatives. And so this would be the result of taking the derivative of the function f of g, and so we're actually going the reverse direction and integrating it. And we know from our experiences in class, this is done by integrating and letting u be equal to g of x, in which case the differential of u, g prime of x dx, appears in the problem. And because that differential appears in the problem, it makes the resulting integral after substitution much easier to handle. So after substituting in u for g of x, we would have f of u, and then this term is just du. But this video isn't going to go over that because we've gone over that several times. This video is going to talk about and dwell on what goes inside the new limits. Because believe it or not, you can't use the existing limits because you've scaled the space that you're working on. You've created a linear transformation. Well, it depends on the function g of x, but you've created some sort of transformation of the space. So the space that you're working on isn't the space that you started with. And because of that, integrating from a to b makes no sense, because if you look at a to b, this is x equal a, and this is x equal b, but in this new scenario, you're integrating with respect to u. So I need to know what u is at b. Well, that would be the top limit. The bottom limit would be what u is at a. So if I look at u at a, that's just the function g at a that I substituted for. And then the top limit is my substitution at b, which is just g of b. So if you put all this together, the resulting answer then by the fundamental theorem of calculus is take any antiderivative of f, so we'll call that capital F, and you evaluate at the top limit minus at the bottom limit. So we're going to do several examples of this, but this is the basic rule, the basic formula that handles how to integrate via substitution for a definite integral. All right, so our first example we're going to start with is the integral from 1 to 2 of 3 times 2x plus 3 squared. Now, the appropriate U substitution to make here is 2x plus 3. You could also FOIL this out, but we're talking about substitutions here. So let u be 2x plus 3, in which case du is going to be 2dx. Now, there's not a 2dx in the problem, there's a 3dx in the problem. And so if I want to substitute for 3dx, how do I turn a 2 into a 3? Well, the answer is you multiply both sides by 3 halves. So this means that 3 halves du will be equal to 3dx, and that's the 3dx that we see in the problem. So when I go to make my substitutions, this will be equal to the integral from some limit to another limit. We'll put in the limits here in a second. 3dx is 3 halves du, and 2x plus 3 squared turns into just u squared. Now the limits are supposed to be the value of u at 1 and the value of u at 2. So if we come over here to the side, u at 1 is, here's my function u, my substitution. U at 1 is 2 times 1 plus 3, or 5. And u at 2 is going to be 7. So updating my limits and pulling out any constants, the new integral is going to be 3 halves, and the new limits are going to be 5 to 7 of u squared du. And so the hope is that we can easily integrate this, and it turns out we can. This is u cubed over 3. and we're going to evaluate that from 5 to 7. So I'll clean that up a little bit, canceling the 3's here. This is u cubed over 2 evaluated from 5 to 7. Now, the thing that I want to mention here that makes this different from indefinite integrals is with an indefinite integral, before we get to the evaluation stage, well, there is no evaluation stage for starters, we would actually back substitute for u. But we don't have to do that here. We don't have to rewrite u in terms of x because the limits we have, 5 and 7, are in terms of the variable u already. And so that limits the necessity for us to transform back into x. If you did substitute back in for u in terms of x, you would have to use the old limits 1 and 2 to get the correct answer because those are the x limits. But here we're going to use the u limits. So by the fundamental theorem of calculus, this is just 7 cubed over 2 minus 5 cubed over 2, which when calculated gives a total of 109. So that is the basic method for using a u substitution to find a definite integral. The main step that's changed is you have to update the limits. So these are the updated limits, and they're the limits in terms of u, right? So updated limits in terms of our substitution u. All right, let's take a look at another example. So this example will be a little bit different. We're going to be looking at the integral from 1 to e. Now this is the base e, the exponential number e, of natural log of x divided by x dx. Now this is sort of a contrived example. It's going to work out really well, but the point of this example is that the upper limit there is an exponential number, and that seems very difficult to work with if we had to stay in terms of x, but we don't. So for this one, your u substitution here should probably be natural log of x, in which case your differential is 1 over x dx. Now, like I said, this is sort of a contrived example, so this works out really well. You've got the d of x over x right here, which is du. Also, we're going to need u evaluated at the upper point, which is e. So u at e is natural log of e, but we know that natural log of e is 1. And also, we'll need u at 1, or natural log of 1, which is 0. So when the u substitution kicks in, this integral is now the integral from 0 from 0 to 1. These are my new limits, 0 and 1. So it's the integral from 0 to 1 of natural log of x, but natural log of x is u, times dx over x, but dx over x is du. So this is a much simpler integral. This is simply u squared over 2 evaluated from 0 to 1, which gives the result 1/2. So a seemingly difficult integral was made very easy by an appropriate substitution, and the limits, which were also somewhat complicated, became much simpler via the substitution. So when you choose a substitution for a definite integral problem, you should be looking at not only how to make the integrand simpler, but also how to potentially make the limits of integration simpler. So this last example will demonstrate that again. We're going to look at the integral from square root of 3 to square root of 8, x times the square root of x squared plus 1 dx. Now here the u substitution that seems appropriate is x squared plus 1, because we know the differential is 2x dx, and therefore du over 2 is x dx. And you can see that the x dx here matches what's in the problem with the x dx there. Okay, if we update our limits of integration, I need to know in terms of u what is square root of 3. So u at square root of 3 is the square root of 3 squared plus 1 or 3 plus 1 equal 4. And our upper limit of integration is going to be the square root of 8 squared plus 1, or 9. So our new limits are 4 to 9. X dx is du over 2. And we simply have the square root of u. Okay. If we pull out the 1/2, then we're looking at the antiderivative of the square root of u, which would be u to the 3/2 divided by 3/2. And we're going to evaluate that from 4 to 9. If I flip 3/2 in the denominator, if I multiply by it, it's the same as multiplying by 2/3. And the 2/3 and the 1/2, the 2's are going to cancel, which leaves me with a constant of 1/3 u to the 3/2, and that's going to be the thing that we want to evaluate here. So if I plug in 9, I get 9 to the 3/2 minus 4 to the 3/2. And remember, when you see something like 9 to the 3/2, the bottom number is the root, so the root is 2, so it's a square root. The top number is the power, so it's 9 cubed. And you can do these in any order. So this is equal to the square root of 9 cubed. You can do the powers and the roots in either order. So I'm going to think of it as the square root of 9 cubed. The square root of 9 is 3. 3 cubed is 27, so I have 1/3 times 27, which is 9. And here I've got 4. The square root of 4 is 2. 2 cubed is 8. And so I have 8/3 here. The net result there is 19/3 for the integral. So the information being provided here is mainly how to handle a definite substitution or a definite integral substitution, and primarily the only difference between that and indefinite integrals is that you will be evaluating the substitution function g of x, which is the u function, your u substitution. You'll be evaluating it at the limits in terms of x to update the problem to limits in terms of u. And if you miss that step, you're going to get the wrong answer. And I've seen that many times before. So make sure that anytime you do a u substitution, if it's a definite integral, you also take a look at the limits of integration and update those accordingly. All right. Thank you for watching.